Okay, so hello everyone, and welcome back to our weekly Python meetings. Today we have the honor of having Maximiliano Blanco, who's going to talk to us about supervised learning and specifically random forest. So thank you everyone for coming again, and go ahead.
Well, good morning, everyone. I'm Maximiliano. Today I will show you the basics of the supervised learning, applications of supervised learning in real astrophysics, and specifically, I will tell you how a random forest algorithm works and a practical example. So let's get started.
We are
We are
entering,
entering, we are living in a golden age for the data domain astronomy.
We are entering
We are entering in a golden age for big surveys and new big volumes of data. In recent years, new facilities and surveys observing or aiming to periodically observe the sky will start to generate substantial archives of data. For instance, today we have the STF, the Gaia mission. Soon enough, we will have the whole data from the LSST and the Plato mission. So to put numbers in your head, the STF and the LSST will observe between 1 and 40 billion objects. This means we will have trillion measurements for these objects. Particularly, the LST will produce 10 terabytes of data each night. That's a lot of data. And in a window of 10 years of processing all this data, we'll have around 500 petabytes of data. That's a lot of data. I have to Google it, how much data it was, because it's a lot. So here we are facing a new problem. There is a data tsunami approaching towards us, and we need to figure out how to manage this data. We have the problem that we will have so much data that we will need to treat it in a different way, because the classical manual way, going star by star or galaxy by galaxy, is not viable for these big volumes of data. So now we can think ourselves, how do we overcome this? What we can do to manage this data in an efficient way? So in recent years, machine learning has started to arise as a possible solution. It's starting to become a very popular solution in the astronomy community. So what is machine learning? There is a lot of definition of machine learning, but they all point to the same idea. We can think of the machine learning as a subfield of computing science focused on building algorithms that can learn from data. We can broadly separate the types of machine learning in three: the supervised learning, the semi-supervised, and unsupervised learning. In a previous meeting, you learned about unsupervised learning, particularly clustering algorithms. Today, I will focus on supervised learning. So what is supervised learning? Well, supervised learning happens basically when the data that I use to train my model is labeled. What is labeled? What it means to be labeled? Well, we know both inputs and outputs. I have my input data, and I tell my model, well, this is the input data. This is the answers of that data. Figure it out how you connect the input and the real answers. So I tell the model the answers beforehand. So the algorithms will learn how to map between the input and the correct outputs. And well, that's basically supervised learning. That's the idea of supervised learning. And one downside of this kind of machine learning type is that we need a lot of training set, and having a big data set that is already labeled is very hard. For example, if you want to predict metallicities, you will need to have a lot of metallicity information beforehand, and that's quite expensive. So that's the big downside of this type of learning, but not everything is lost. This is a visual way that you can understand how supervised learning works. I have my level data, in this case the different shapes, and I tell my model, well, these shapes correspond to a rectangle, this one to a circle, this one to a triangle, and this one is an hexagon. So I put this information in my algorithm. I will train a machine learning model. I will obtain a machine learning model. And then after the training, if I put a new unknown data, in this case, I tell to my model, well, I have these two shapes. I don't know what are those. Can you make a prediction? And if my model is well trained, I will obtain a prediction. In this case, this is a triangle. This is a circle. So to put some real examples, for in this paper, they obtain stellar atmospheric parameters and chemical abundances for 5 million stars using a photometry from S+. And you can see here how powerful these tools can be, because doing obtaining spectroscopic data for 5 million stars is impossible. So using photometry, which is very easy to obtain in comparison with the spectra, you can obtain proxies or approximation of these stellar atmospheric parameters. Another good and big example is the Alerce broker system, the light curve classifier, which will be classifying the light curves of variable objects in the sky for the Vera Rubin Observatory. So it's a big deal. And Alerce basically gets an alert. It says like, well, this is an object that is varying his luminosity in the sky. The Alerce will take this information and will first classify them in 3 principal groups. And after that classification, we'll also classify them in the different subtypes of each group. So it's very useful, and it's an automatic classification. So it will produce this information every day. So now you can think, well, maybe these algorithms are very hard. They are very complex. I will never understand it. But that's actually not true, because Alerce use a very simple algorithm called random forest. What is a random forest? Well, basically, it's an algorithm that works building many different decision trees and combine them. What is a decision tree? Well, for example, in this diagram, we have 1, 2, and 3 decision trees. A decision tree is a machine learning algorithm that takes the input data and start to do partition, start to split the data using some criteria. It can be, for example, in this first split, you can say, well, in the left will go all the rounded shaped fruits, and on the right, the non-rounded shaped fruits. It will start to separate the data to obtain a prediction. So it start to generate the so-called leaves and generate this tree architecture. So how the decision tree decides what split to do? Well, it basically tries every possible split until it finds the one that makes the better prediction. So the forest part in the random forest name is because it uses many decision trees to obtain a final prediction. For example, the first tree will, I don't know, if I pass an apple, the first tree will say, well, this apple satisfies this condition, and I think it's an apple. This fruit that you are passing me, the second tree will say, this fruit that you are passing me satisfies this condition, and I think it's an apple. The third tree will do the same and can say, well, this is a banana. So how you do your final prediction is a majority voting. So that's the forest part of the name. The random part comes from the fact that each tree doesn't use the whole data. It uses random subsamples of the data. So the first tree will not receive all the fruits, will receive a random set of fruits. And also each tree will not use all the features of the tree. I can say that the first tree, well, you use the color and shape to separate the data. The second tree I will say, well, use the taste and I don't know, maybe the density of the fruit. So every tree uses random subsample of data and features. This is called the bootstrap sampling. So that's why it's called random, because it uses many random trained trees. It's a forest of decision tree. They didn't complicate very much with the name. So that's the idea behind a random forest. So I did too much talking. Let's go to the fun part and let's start to do a practical example. I think, okay, I have this, I prepared this notebook. I can upload it later. So first, here we are using the data from this article, which is basically a compilation of different photometric data and also redshift measurements of galaxies. So here is the data that we have. We have the photometry of around, well, not a lot of galaxies, but we have the photometry of these galaxies, and we also have a measurement of the redshift of the galaxies. Okay, this is like the real redshift of the galaxies. So first, you want to do when you train any model, you want to check what are you working with, because if there is any outlier in your data, your model will fail or will do weird things. So it's wise to always see what is your data. Here, the photometric distribution are very beautiful, so we are not have any outlier, but I don't know if we have a source with 100 magnitude. Well, that's weird. So maybe it's an outlier. You need to clean the outliers. So now, afterwards, we define our features. The features are the data that I want my model to use to make a prediction. In this case, we want to obtain photometric redshift. So this is the features, the photometry of the galaxies. And the target is the thing that I want to predict. In this case, I want to predict the redshift. So here I will use the scikit-learn model, which is from a scikit-learn, a very popular machine learning library. So here, the first thing that we do is to split in a training and a validation set. You don't want to use all of your data to train your model, because your model can do very well predictions for your training data. But if I put an unknown data, it will do weird things. That's called overfitting, because in some cases your model will predict very well your training data, but because it's cheating, it's telling, well, this is the input data, and I look for the answers. Okay, these are the answers. So it doesn't learn. So it only cheat the answers. So you want to use a fraction of your data set to train and another fraction to see if it is working. The validation set, the machine doesn't know the validation set, so it's unknown to the model. So here I define the training and the answers of that training data set, and I create the model. In this case, I am using a random forest regressor, which is basically a random forest, but it makes prediction of numeric values. And with these 10 lines of code, you already do your first machine learning model. So only with 10 lines of code, you have become one of the 10 most dangerous hackers in the internet history. So now I define the variables for my validation set. And well, this line is important because if you have a big model, I don't know, you train your model for like 2 days. You don't want to train the model 2 days every time you open your computer. So when you train your model, it is wise to save your model to use it later. So how we evaluate our model? There are many ways to evaluate them. I will use these two metrics, which basically tell us the error between the real value that I want to predict and the prediction. So here I evaluate the model and obtain these errors. I don't know if any works with Galaxy, how big an error of, I don't know, 0.1 redshift is. I think it's small, but I don't really know. I suppose it depends on the case. So these numbers by itself doesn't tell us much information, so we can plot our results in this way. So the y-axis is the prediction and the x-axis is the real value. So as we can see here, most of our values follow this one-to-one relationship. So the model that 10 lines of codes, it's predicting very well the photometric redshift. So we can ask ourselves, well, how do we obtain the best parameters? Well, there is many ways. You can do it by hand, trying different combinations. But if you want to make your life easier, you can use, for instance, this function, which is a randomized search. I define like a grid of different parameters that I want to test, and the randomized search will do random combinations until it finds the best. There is another function that tries every possible combination, but if you have a big grid, it will take like forever. So if you have a big grid, it's better to do a random search. You run this search. I don't run it here because it takes a while to do. And in this case, the model says, well, these are the best parameters that you need to use. And I test the model that it predicts that has the best parameters. And actually, in this case, we found a bigger error, like 0.01 redshift. Like it's a little bit worse. So we can compare our both models. They look almost the same. Actually, the one that says has the best parameters is a little bit worse, but I think it's because I am using a defined random seed to it. If you do many iterations, you will find a good machine learning model. So that's the basic idea here. With this notebook that is very short, you have like the basic stuff to incorporate to any work you want to do. So well, that's basically everything. So what are the messages to take home? Well, machine learning is very useful to manage a lot of data and to obtain, I don't know, prediction of parameters that will be hard to obtain one by one. For example, redshift. You don't want to look for the redshift for individual galaxies if you have a lot of galaxies. And training a model is not that hard. The idea behind a random forest is pretty simple. So when you go to the literature and the documentation, you will see you will know, well, what is a leaf, what is a split of the data, and so on. So that's basically what I wanted to tell you in this session. So thank you.
Thank you. Does anybody have any questions? Yes,
Do
go ahead.
you use this in your research? Do you use in your research?
I use these kind of models for my research. I wanted to try to look for photometric metallicities, and it didn't work very well because we use a model created by a collaborator of us. The thing is that we wanted to look for very metal poor stars, and the data wasn't trained for that kind of stars. So it made a prediction, but it wasn't very well. So yes, I used some of these models, but you need to take into account how it's trained and how it's built before you do it. It's not a black box. So I used it. It didn't work very well, but we tried.
How do you know?
No, go ahead.
How do you know the predicted sets are like good or not?
Yes, to tell how good is our model, we use the metrics. There are many metrics. It depends on what are you doing. In this case, we're predicting like values, numerical values. So we can use these metrics, which tell us basically what is the difference between the predicted value and the real value.
But for that you can only do when you have the real value, right?
Yes.
Okay. So you have a model, then you put it in like the known values that you want to, and
yes,
it gives you a prediction.
Yes, yes.
So as you can see that one by one plot there is a lot of scatter, right? So
yes,
you know if like the known value is good or not. Is there like a parameter?
Good.
Or is it just like if your model is bad, this we can't trust it?
Good question. Well, you get an estimation of how good is your model using the validation set. But afterwards, well, you're right. You can have, I don't know, a point here. So the idea is that if you had like a good prediction for your validation set, and then you want to try it like unknown values, you will never, well, you will have a prediction, but you will need to take in account, well, the values here, well, the values that I want to test are the ones that lies in this line that are similar. If they are similar, you have like a very big chance that the prediction that you made is good. So you need to look for that things that are very similar to the ones that follow this line. So it's an approximation. This will never like be better. Will have very precision like the real value itself.
I have a question similar to that one because I know that I've never used random forest, but I know when you, instead of like for finding numerical values, you try to classify it, it gives you like a score because of the different votes of each decision tree. And there you can see like if you trust or not your result. I don't know how it works here. It gives you, if we could look at those strange outliers and see if they have a low probability, but it's still over 0.5.
Yes, that's a good like a good point to take into account. For classification, yes, you have like a probability of belonging to that class. But in here, you can use numerical metrics, see how your model behaves, like in a general way. And then if you apply it to similar data, you should have like that kind of precision. So it will never tell you the real truth. You will have to go and measure the real redshift, but it's a good approximation. It depends of what you want to do, because if you don't need like a very detailed precision, it's good enough.
How large a data set would you need to start thinking?
That's a good question. Like a rule of thumb, you will always want to use as many data as you want, because the most data you have, the better model you can get. So how much, it depends on what you want to do. If you want like a very precise model, you will need a lot. I don't have in mind like a exact number, but the better you have, the better model you get. So
you wouldn't apply it over a data set.
yes, because I don't know, you want to measure like photometric metallicities and you only have like 100 stars, you will probably get very bad predictions. So the idea is to see how good your model performs in general. So that's why we always test the validation set. So yeah, if you have very like a small number of data, it will not work very well.
There's a question in the chat. Oh, I can read
yes.
it. Priscilla asks, does it work for distinguishing by model, data, or distributions?
Like to do classification, or?
I guess that's the question.
Actually, yes. In this case, I predicted numerical values, but you can use this. Random forest can actually do classification stuff. So, for instance, going back to the fruit example, we can predict which class the input data has. So this is similar to Alerce. Alerce doesn't predict numerical values. It classifies in different class. So yes, if you have data that belongs to a class and you tell your model which class belongs the training set, you will get prediction of classes. And the workflow is almost the same. The only thing that changes are how you evaluate your model. So yes, you can use it to classify and do that kind of stuff too.
I have a question. So I've been thinking, because I work with our stars, of some way of trying to, because as of now, Alerce, for example, is only classifying into variable stars, stochastic and transients.
Yeah.
And so there's some people that are already doing this, and they're trying to get the data themselves live from LSST, or maybe filtered by Alerce, and then apply it themselves at a random forest or whatever to find our outlier stars quickly. So do you know how you would approach the fact that the only classification that I care is whether it's an outlier star or not? How much training data that is not an outlier star should I use? Do you understand the question?
I think so. Well, if you want to, random forest is very good at separating classes. Actually, the classical way to use it is like, I have this class that I want to predict, and the other things that are not in that class. So you can do that, and how much data you will have. You always want to have a balanced data. So you want to have like the same amount of RR stars and the same amount of non-RR stars. So if your data set is like homogeneous enough and have the same sizes, you will perform a very good model. So that's the idea.
Thank you. Any more questions? Okay, then let's give an applause to Frankie. And we will see you in 2 weeks because we have Semana de Receso. Thank you.